Hi everyone, in this video we're going to present our machine learning final project and our topic is home credit default risk. As of September 2018, the total amount of household debt in Hong Kong was valued at 253 billion USD, and the different types of household debt include auto loans, student loans, credit card loans, and private loans. Since the subprime mortgage crisis in 2008, loans approvals have become difficult to obtain for individuals with insufficient or non-existent credit histories. So our goal of the project is to make use of a variety of alternative data, such as telco and transactional information, to predict the probability of default of a loan application. Our prediction result will be evaluated based on the area under the ROC curve between the predicted probability and the observed target.
The dataset we are using contain different information about the client and the credit application. There are a total of 221 columns in 7 different tables. The tables are related to one another through foreign keys. This set of data is difficult to handle because we need to find a way to merge these different tables without losing any significant amount of information. This diagram shows how the 7 tables are related. The table in the top of the hierarchy is the main table for the applications. Each application is a row in this table. The prediction, that is the output of our machine learning models, is for each row in this main table. All other tables are related to this main table either directly through foreign key or indirectly through other tables in the middle layer of the hierarchy. For simplicity, we will call all tables other than the main table as secondary tables or supporting tables.
Now I'm going to talk about some of the data exploration we have done on our dataset. From the right-hand side, you can see a pie chart that shows the distribution of the target label, where 1 means the client has payment difficulties at least once before, and 0 means the loan was repaid on time. In this case, the percentage between the two class labels are highly imbalanced, meaning that standard accuracy can no longer measure the model performance accurately. Also, model training will be much trickier. So in order to deal with this issue, we've decided to utilize the downsample majority class technique to prevent majority class from dominating during model training. More details of the technique will be discussed in the later section. Other than the target label, we've also selected some features that could have a considerable amount of impact or correlation with the target. The day's birth features encode the client's age in days related to the application time. By grouping the age group into 5 years per bin and plotting it against the average of the target, we can clearly see a trend where the percentage of default risk decreases as age increases. This means younger applicants are less likely to be able to repay a loan compared to the older age group. From the graph on the top right-hand side, we can see that data points of the loan credit amount feature are mostly concentrated on the left side, which means the mean is larger than the median. In this case, the distribution is considered positively skewed. The issue is that certain machine learning models are very sensitive to the skewness of the data. In order to deal with this issue, we decided to apply log transform to the feature, which is a very common correction technique used to correct for positive skew. The resulting distribution on the bottom right looks a lot closer to normal distribution, which is the decided outcome of the skew correction. The correlation heat map allows us to visualize the correlation between different features and the target label. In this case, we have selected 8 out of a few hundred features that have a pretty high feature importance score based on the light GBM model. We can see that the 3 external source related features have the strongest negative correlation with the target, and the sum of the 3 features account for almost 50% of the correlation. According to the documentation, the 3 features are normalized scores from the external data sources. Although we may not exactly know the meaning, we at least know that as the value increases, client will be more likely to be able to repay their loan. The rest of the features all have a slightly positive correlation with the target, but this is not as significant compared to the 3 external source features.
We need to pre-process our data before using them to train our models. First, we need to merge all the 7 tables into one because most machine learning models expect one single table as input. We found that each secondary table has a many-to-one relationship with the main table, so we decide to aggregate the records in these tables by foreign key. We then calculate a few simple statistics on the aggregate results and create a column in the main table for each of these statistics. The next step is to fill the missing values in the data because a lot of models do not allow missing values in training and test data. We inspected the columns one by one to understand their meaning and decide the best value to use to fill the missing values. For most of the columns, we use median of the column, mean of the column, or just 0. There are also a few columns that require special treatment. One example of customizing the missing values is for the columns about the type of a previous application. This column comes from a secondary table about previous applications. Missing value in this column means that the applicant does not have any previous application, so we introduce a new categorical value for missing values to capture this information. Other than just filling missing values, a few columns require some special transformations. This transformation include like turning invalid values into missing values and dropping columns that do not look like ID, but are actually an ID column, like this month's balance column we show on the slide, which is just an ID of the month. After all these previous steps, the data are in a form that can be used to train our models. But we found that the target label in the training data is highly unbalanced, with only 8% positive and 92% negative. If we train a model directly on this dataset, the prediction will be biased towards negative labels. So we apply undersampling to correct this bias. We divide the training data into different parts, with each part containing the same 8% of positive training data and another 8% of negative data. The negative data are drawn without replacement, so each part has the same positive training data but different negative training data. After that, training and validation are then performed independently on each of these balanced parts.
As mentioned, there are several secondary datasets other than the main table. These datasets usually have multiple records for each applicant in many-to-one relationship, which means that they cannot be directly merged to the main table for model training. Our solution here is to aggregate the fields grouped by the applicant ID. For numeric variables, we will do min, max, average, and sum, while for categorical variables, we would only do the counting on the class label. Apart from aggregation, we also create some new features by cross-field operations. In previous application dataset, we create a field called credit application ratio, which reflects home credit's past evaluation on applicants' ability to pay. Numbers of application field is for counting the frequency of application in the last month, last half the year, and past 12 months. For installment dataset, late payment days was created to see how many applicants seriously late payment records. Early payment was treated as 0-day late for payment. On the other hand, payment installment ratio reflects the ratio of how much was not repaid by the applicants in previous installment. Average amount drawing or buying goods are two separate fields to track average credit card usage behavior of the applicants per transaction. Special expense is more of a threat to show if the applicant has some uncategorized usage with their credit card. Drawing for goods ratio shows the main usage of credit card for the applicants if it is more on buying goods or drawing cash.
In this section, we will introduce the 4 models that we implemented for the project. The first is logistic regression. This is the benchmark classification model and it will be used as our baseline for performance. The remaining implementations are varieties of tree-based classification algorithms. This includes random forests And finally, we also look at two popular gradient boosting tree algorithms, LightGBM and XGBoost.
The model we will focus on is LightGBM. LightGBM has gained traction in recent years due to training efficiency, low resource usage, and relatively high accuracy. It is a type of gradient boosting algorithm, meaning that it trains an ensemble of models sequentially, with a later model predicting the residual, or error, of the previous models. It works by growing trees vertically, identifying the leaf with the largest loss to grow. This is different from many other boosting algorithms that grow the tree level by level. This difference allows LightGBM to reduce more loss. On top of this, it has exclusive feature bundling, which means it bundles mutually exclusive features to eliminate feature redundancy.
Tree-based algorithms such as random forest, LightGBM, and XGBoost use the concept of importance score to measure feature importance. These scores look at the decline of the out-of-back accuracy if a feature is randomly dropped. If the accuracy has no significant decrease after dropping the feature, it means that the feature is not important for the prediction. Bayesian optimization is a popular machine learning parameter tuning method. It builds a probabilistic model using Bayesian inference and Gaussian process to qualify and to maximize the result. The tuning process has two parts. Firstly, the Bayesian posterior probability distribution will be built based on the training dataset, and second is to find the parameters that maximize the learning schema. The ROC curve is what we have decided to use as our evaluation methodology. The ROC shows the performance of a classification model at different false positive rates. In other words, the ROC shows the trade-off between sensitivity and specificity. We will use the area under the curve of the ROC curve as a measure of accuracy of our classification model. Visually, a random classifier has an area under the curve of 0.5, whereas a perfect classifier has an area under the curve of 1.
Our approach starts with training different types of model on the preprocessed data without undersampling. Then we perform undersampling and repeat the training to check if there is any improvement. We also pick the model that gives the best results to further perform feature selection and hyperparameter tuning. The output of our model is the probability of credit default. We performed 5-fold cross-validation on the training data and plotted the ROC curves for each of the models. Since they have similar shapes, area under curve is already a good performance metric. For special cases like the curves having different shapes in different regions, we might need to use some other metrics, but for this particular case, area under the curve is already good enough. Here comes our results. The scores shown here are all area under curve. As expected, the baseline logistic regression model gives us the worst results, having the lowest score, while the tree-based model gives better results. LightGBM and XGBoost give very similar scores, but LightGBM is slightly better, making it our best model. One important point to note here is that all of our tree-based models perform much better when trained using our preprocessed data, compared with the Kaggle kernels that do not preprocess the data much. That means our preprocessing and feature engineering significantly improve the results. However, logistic regression performs worse when trained using our preprocessed data. One possible reason is that our preprocessed data contain more features, and a linear model like logistic regression does not work well when there are too many features.
Here are the results we obtained after performing undersampling. We train a model using each of the undersampled parts, and then get our final results by averaging the predicted probability of each part. From the table in the bottom, we can see that our results indeed improved after performing undersampling, especially for random forests and logistic regression.
The figure on the right shows the top 50 features importance given by the LightGBM model. The most important feature is the age of the applicant in units of day. We found that most of the top 50 features are those created by us, mostly statistics of the supporting table aggregate. We tried keeping different numbers of features, starting from the top 50 and increasing the number in steps of 50. We found that keeping only the top 550 features give the best results, So we use only these 550 features for further model tuning. We found that the improvement for dropping non-important features is not quite significant, but it does give us the benefits of shorter training time. This is important because our dataset after feature engineering is larger than 1 gigabyte, so it takes quite a long time to train, especially during model tuning.
Finally, we choose light GBM to be tuned by Bayesian optimization to obtain a set of hyperparameters that works best on coarse validation. The parameters we tuned are shown here. Their ranges are set under the empirical experiment. We found that using the undersampled data in evaluation function can obtain a better parameter set instead of using the whole dataset. The best tuned setting can obtain improved Kango score. To conclude, we start our project by exploring the dataset provided to us. Then we merge the 7 tables in the dataset, clean the data, filling missing values, and engineered some new features. We then train different models and select the best one based on area under the ROC curve. We then performed undersampling, select the best features for training, and performed Bayesian optimization for parameter tuning to obtain the best results.